function f of x on some given interval. So what we said is that we divide the interval AB into, this is the most simple way, is to divide the interval AB into sub-intervals, okay? So now here I change a little bit the notation perspective to next time, to last time. So if you want, I will record a video corresponding to the last session just to correct these notations. Okay, so last time I used n, capital N, as being the number of points. Here I will use capital N as being the number of sub-intervals. So if you have n sub-interval, you have n plus 1 point. It's the same thing. If you have n points, you have n minus 1 sub-interval. If you have n sub-interval, you have n plus 1 point. Okay, it's just like to have h equal b minus a over n and not n minus 1 here. Okay, so we'll use here after n as being, capital N as being the number of sub-interval and not the number of points. The number of points will go till n plus 1. Okay, so we saw that for the rectangle method, okay, so if we have points going from 1 to n plus 1, so you have n sub-intervals. So basically, okay, the left corner approximation consists of summing these rectangles with, okay, the height of the rectangle being the left corner of the function, and f from f of x1 till f of xn, if we have n plus 1 point here. So from 1 till n, f of xi. And here it will go from 2 till n plus 1. Just create this. Till n plus 1. Okay. From this point to this point for the right corner, and from the midpoint approximation, okay, it's from 1 till n here, h of f of xi plus h over 2, the midpoint approximation. All right, now what we saw is that this is the general the general expression if we have a given number of points or a given number of sub-intervals, so you can evaluate the integral. But if we don't want to specify in advance the number of points and we don't want to recalculate from the beginning, so we can develop an iterative approach. So the iterative approach, as I explained, is that we start by, why this is, okay, so somehow the animation was is not valid anymore. Deleted the animation or something like this. Okay, so it doesn't matter. So basically you start by, okay, one interval, so I1 is equal hf of a, and then you double the number of sub-intervals, so n equals 2 here, and then you get here for the left corner the sum of 2 points, so b minus, so h is divided by 2 with respect to the first one, and then you have it's b minus a over 2 and h, f of a plus b over 2, the midpoint. And then you can express this as being this first, the integral of the first step over 2 plus h f of a plus h. If you take at step 3, you double the number of sub-interval, so you become n equals 4, and then the same thing, okay, you can express as f of a plus b over 4, f of b plus b over 2, f of 3a plus b over 4, yani f of a plus h, f of a plus 2h, f of a plus 3h. Now the f of a plus the f of a f of a plus b over 2, this is included in this integral, so you can express this as being I over 2 plus the sum of the odd term here. So at every step n here, you're dividing the step by 2 and you're multiplying the number of points, the number of subinterval by 2, and then you're using the previous integral over 2, okay, the previous approximation to the integral over 2, and you're summing the odd term. Okay, so this is what I explained last time. So here now for the algorithm, just to see it, let's عليها شوية. واضحة. Okay. Okay, so now for the algorithm, okay, you start by defining a and b, epsilon and f, okay, the functions, and the interval and the precision that you want to reach. So you start by constructing the first integral with one subinterval, yani just the interval ab. So h is equal b minus a, I is equal h f of a. So this is for the rectangle left corner approximation here. I'm using it. And then h is equal h over 2. And then I is equal of I over 2 plus h f of a plus h and a plus b over 2. Okay, so this is the second step. So at this point here we have two subintervals, right? So n equals 2. Now I will repeat this. I will divide the subinterval by I will multiply the subinterval by 2 till I reach I1 minus I is inferior to epsilon. So when it is superior to epsilon, it continues, okay, dividing by 2 the interval and calculating using the previous integral over 2 and using summing over the odd term. Okay, so this is a while loop. While I1 minus I superior to epsilon, okay, you enter the loop. You save the previous here, I equals I1, so you save the previous integral corresponding to the previous step. You divide the step by 2, you multiply the number of points by 2 here, and then r equals 0. Okay, r will be the sum of these all term, and now you will do a for loop. So you will do a for loop for k equals 1 till n over 2. Okay, because in this expression I had a sum till n over 2 here for the odd term. Okay, so r is equal r plus f of k a plus 2k minus 1 multiplied by h. Okay, this is, the parenthesis should be after the h. Okay, I'll correct this. Okay, I'll correct this later. Okay, here there's a parenthesis here, f of a plus 2k plus 1 minus h. Okay, and k equals k plus 1 is just like the for loop. In the for loop, k is equal to k plus 1. So this is generally when you write a for loop in an algorithm, you write it as a while loop. But when you write the program, it's better to write the for loop here. Okay, and then when you exit the for loop, okay, sorry, okay, here you make I1 is equal I over 2 plus H, okay, this quantity here R, okay, and that's it. Now I'll show you the program. So open MATLAB. Okay, so let me share this. Share. Right. عم تقشع المطلب.
Yeah.
So basically, here I defined, okay, so the precision, okay, A, B, and then, okay, here I use f sinus x that I integrate between 0 and pi over 2, right, in this example. Okay, so my f of x, I define the function y equals f of x, y equals sinus x. You can use any function here, okay, for the integration. Okay, because here you call your function. So h is equal b minus a, I is equal to h f of a. Okay, h is equal h over 2, so I divide by 2. All right, I1 is equal I over 2 plus h f of a plus b over 2. This is the error. So here I defined it in absolute value. Yani, error being I1 minus I over I1. Okay, so you can, this is called absolute precision. Okay, we can define it, this is relative precision. We can define the absolute precision, yani, I1 minus I. So I must take apps here. Okay, so it's apps I1 minus I. So the number of iteration is equal to 0, okay? And now here the number of iteration must be equal to 2, excuse me.
2.
Yes, n equals 2. This is the number of some sub-interval. Okay, so I equals I1, the number of iteration is equal to the number of iteration plus 1. So, okay, this is just to see how many iteration it needs to get the result, okay? So R equals 0, H is equal H over 2, so I divide H by 2, okay? And now here, the N equals to N, I don't know why it's in the end, it should be in the beginning. We will see if it's correct or not. I forgot why I put it in. And so for k equals 0 till n minus 1.
N over 2?
Sorry?
Is k going from 0 to n over 2?
Yes. Till n over 2. So it's 1 till n over 2, right?
Mm-hmm.
k 2k plus 1h, right? I think I used a different formula before. Okay, so I1 is equal I over 2 plus h multiplied by r, and the error is the absolute value of I1 minus I. Okay, and now let's run this program and see what happens. So what is the result? So I1 just يعني انتوا ما بتشوفوا هذا بس just to see. I1 is 1. There's something maybe wrong here. Okay, let's take 6 here. I1 and just like في precision شوية نشوف from this here. Just try to run. Okay, so I1 here, I get 0001. It's correct. So now this is correct. Okay, now because the integration of sinus x, right, from 0 till 1, okay, must be equal to 1. From 0 till pi over 2 must be equal to 1, right? Because it's cosinus x between 0 and pi over 2, cosine of pi. So it's minus cosine x between 0 and pi over 2. So cosine pi over 2 is 0 minus minus 1, so it's 1, right? Integration of sinus x between 0 and pi over 2. So here I got, if I apply this program, I get 1. But the important thing is to see here what is the number of iterations. So number of iterations, how many times did he go into this while loop? So let's just like print this number of iteration here. Okay, it's printed. هذه شو بدنا فيها هذا نشيلهم هذول. Okay. So you get 19 iterations here. Okay, to get the result, we need 19 iterations. Right, now we would see another method, which is more accurate than this one, which is called the trapezoidal method. ماشي الحال؟
Yes.
Okay. إذا بدكم فيني أفرجيكم السكرين تبع that I get here, that I got. Okay, so I got number of iteration equals 19, and for the integration I get 1.0001, and I had that precision 1e minus 4, so he gets, okay, a result that is accurate up to 1e minus 4 after he stops. All right, so now let's look at another method. Okay. So the trapezoidal method. So as the rectangle here, the trapezoidal similar to the rectangle, but instead of approximating the sum of the integral as a sum of rectangle, here you use the sum of trapezoids. So, sorry. Okay, so you will sum these trapezoids. Okay, so if you have n plus 1 points, you have n trapezoids here, right? That correspond to the number of sub-interval, which is n in this case. So you have n trapezoid. So you are doing I is the sum from I equals 1 till n I. Okay, so this is I1, I2, I3, I3, I4, IN, etc. Where I is the integral or the area of the trapezoid constructed upon the points xi and xi plus 1. Okay, so what is the area of a trapezoid? Okay, so the area of the trapezoid is 1/2 the sum of the base. Okay, the two base here, the sum of this. So this is f of xi plus 1, right? And over 2 multiply by, okay, the height.
The height.
So the II is h over 2 f of xi plus of x f of xi plus 1. Okay. Now, for example, for this trapezoid is f of x1 plus f of x2 over 2 multiplied by h. Okay, so we have the same h. Now, so the total integral here is the sum of these, okay, area of the trapezoids. So it's the sum of the II from I equals 1 till n. So it's h over 2, the sum I equals 1 till n, f of xi, f of xi plus 1. Now I will just share a new screen to see, okay, to show you how we can recast this equation. Okay, I'll show the screen.
Yes.
So we have that the integral is the sum h over 2 f of xi plus f of xi plus 1. Okay.
دكتور بس سؤال، هود السيشنز اللي عم بتصورهم رح تنزلهم كمان يوتيوب ما هيك؟
يا رح ابعث لكم اياهم يعني على الدرايف تنزلون.
اوكي ديل ميرسي.
هلا بشوف يعني يا يوتيوب. Alright, so it's I equals 1, but it's good that you take notes كمان يعني. Okay. So but I will surely on YouTube or send you the link to download. So I equals 1 till n f of xi plus f of xi plus 1. All right. So this is now if I want, so f of xi, the sum, okay, I can write it like this. F of xi plus the sum I equals 1 till n. Xi plus 1. Okay. So here, okay, if I take the sum from 2 till if I take the sum from 1, okay, so before doing that, we'll leave this like this, f of xi, and then here we want to convert it as something as f of xi. So here, if I put I prime is equal I plus 1. I not then I will have here, okay, the sum from so I prime sum of x I prime, okay, till n minus 2, okay, from I prime is equal n minus 1, sorry, from I prime is equal to 1 till n minus 1. That's good.
Yeah.
Okay. So
لا from 2 to n minus 2 معك.
from I prime is equal to, sorry, yeah, from I prime is equal to 2 till n plus 1. Yeah.
Yeah.
Because if, yeah, from 2 till n plus 1. Okay, so now here what I will do is that here I will extract, okay, the f of, so I want to express this quantity as this one, because, okay, you can always recast here I prime is equal, yani I can re-express this here like this as, instead of I prime I will reuse here I, okay, so it's the same thing, yani. Okay. Okay. Now I want to express these two quantity the same way. So what I will do is that I will put out of the sum the f of x1. So it's f of x1 plus the sum of I equals 2 till n. Yes, n plus 1, not n plus 2. So the sum is equal 2 till n f of xi. And here I will احطلي على برا ال f of xn plus 1. Okay, xn plus 1. Okay. Plus the sum of I equals
2 to n.
till n f of xi. This is just to have here the same sum here. Right? So now this I can express it as the same sum. So that just that you see that here now what I get is equal h over 2 f of x1 plus f of xn, okay, plus 1, excuse me, okay, plus h, the sum from I equals 2 till n, okay, of f of xi. So basically now if we compare to the rectangle methods, okay, so
H over 2.
no, because it's 2 time here, so we have 2 times.
صح صح صح.
Okay, we have 2 times, so h over 2 becomes h.
Okay.
So now if you just like if you compare, okay, to the rectangle left corner, شو كان عندنا بالrectangle left corner we had, so this was the rectangle left corner, okay, so the rectangle left corner we had h, the sum of, okay, f of xi, with I going from 1 till n, yes, for the left corner, and for the right corner, okay, we had that I is equal h, the sum I equals 2 till n plus 1 here, okay, f of xi. So if you compare now the two methods here with this one, you find out that as we call this I left, I right, okay. So these the two approximation for the rectangle using the left corner and the right corner. If I compare the two, I find that the I corresponding to the trapezoid is IR plus IL over 2. Yani the mean value of these two quantities. If you take the mean value of these two quantities, okay, you find the trapezoid. It's funny because geometrically it looks different, but if you look into the calculations, okay, it's the mean value, and it doesn't differ from the rectangle only by this term here, okay. So this would be the rectangle, okay, approximation. So basically, the rectangle left corner and right corner, in any case, they differ just by this term, the beginning of the first term and the last term, okay, in the sum. So the one used the first term and the other used the last term, but the sum from I equals 2 till n is the same, okay. Only what changes is the first term and the last term. So here, okay, it's equivalent as, okay, a rectangle method, but okay, instead of taking here, you take the first term, here you take the last term, you take the mean value of the first term plus the last term multiplied by h. Okay, so it's as you are doing the mean value of these two values, and it's normal that it will give you a better result, but because, like we said, in case where it's increasing, okay, the rectangle left corner over approximate, under approximate, and this one over approximate. So if you take the mean value of the two, then you get better result. And same thing when it's decreasing, this one over approximate, this one under approximate, okay. And then the mean value of these two methods will give you a better result. And this is a funny result that, I mean, the trapezoidal methods and the rectangle methods are related somehow, okay, even though when you look at it geometrically it looks different, but it's nothing more than taking the mean value of these two values. All right. Okay. So now if we want to so the trapezoidal consists of taking h over 2, the first point plus the last point, plus h, the sum of these other f of xi. Okay, so now if I want to develop an iterative methods for the trapezoidal method. So I have, as before, we had these 2 points here, a, b. Okay, and so the first step, so n is equal to 1, okay, and I have as an approximation, okay, let's take let's say my function f of x is something like this, just like, okay, let's say that the function f of x, so this is my function f of x, okay, and so the first step, I just have this sub-interval AB. For the rectangle left corner, I had this rectangle here. Okay. Now, in this case, I have the trapezoid. So this is f of A, f of B. Okay, and then we have, okay, this trapezoid here. Okay. So at the first step here, I have h f of A. So I'll call this I1 as h f of A plus f of B over 2, right? This is the first step.
Mhm.
Okay. So at the second step now here, okay, okay, so I divide my interval in 2 here. So I get C here equals A plus B over 2. Okay. Okay, so the first step, H was B minus A. And I1 was H over 2 plus H. So at the second step, okay, so I get now here, this is f of C, okay, and now my integral becomes this trapezoid here plus this one here. Okay, so okay, so I have the area now of these two trapezoids. Okay, so the I2, like we said, it's the first point plus the last point over 2. Okay, so here H becomes H, yani, this is H1, this is H2 is equal to H1 over 2. We divided the H by 2. Okay, and of course the N here is, we have two subintervals, so N equals 2 here in this case. Okay, so the I2 is H over 2, the last point plus the first point, same thing, plus f of C, okay, H f of C, okay, plus H, the sum of f of xi, like we said. So it's H over 2, okay, f of A plus f of B, plus I can write it this H f of A plus H, okay, this is H in this case, okay. Or H2 to be more precise, H2 plus H, okay. This is H2, H2 if you want to be more precise. Okay. Now in the program, I will not write H2, just write H is equal H over 2. Okay, the previous, this will make that H is equal, the new H is the previous, the previous H over 2. So, and the same thing, N equals to N, we will write N equals to N. Okay, now the third step, same thing, we will have, so I3 is H over 2, the first point, sorry, I didn't finish here. Okay, for the second step, I didn't finish. So this is here because H2 is equals H1 over 2, so this is I1 over 2 plus HF of A plus H. Okay, so etc. Now for the third step, okay, for the third step, we divide our interval in 4 subinterval. Same thing here. All right, so this is the same thing. Okay, so we have the sum of these 4 trapezoid now. All right. Okay, so this 4 trapezoid. Oh, in any case, you understood my points. Okay, so we have the sum of these 4 trapezoid now. Okay, so R3 is the same thing. So you have H over 2. So here you divide it. So H3 is equal to H2 over 2. Okay, N equals 4 and a 2 times, okay, the previous N. Okay, and so it's H3 over 2. The first point plus the last point. F of A plus F of B, plus now H by, okay, F of, this is A plus H, okay, well here it's H2, okay, so F of A plus H3 plus F of, okay, A plus 2H3 plus F of A plus 3H3. Okay, and that's it. So I have 5 points here. So this is F of A plus H3, F of A plus 2H3, F of A plus 3H3. But هيدي because 2H3, so let's rewrite this as the following. So it's, as I write, H3 is equal, so it's H2, H3 is H2 over 2, so this is H2 over 4, F of A plus F of B, right? Now, this here, 2H3, so 2H3 is 2H2 here, right? This was H2, okay. Now, 2H3 is H2, so this is also H2. Okay. Now, right, so this is H2 over 2, H2 plus H2 over 4, right? Plus H2 over 2, okay, F of A plus 2H2 plus H2 plus the rest here plus H3, okay, F of A plus H3 and plus F of A plus 3H2. So basically what I'm doing is the same method that I did for the rectangle. So this is basically, okay, this is I2 over 2. Okay, this is I2 over 2. Okay, height was I2. So it's I2 over 2 plus, okay, H3, okay, F of A plus H3 plus F of A plus 3H3. Right, so we get at the end the same formula that we get for the rectangle. So the general formula for a step n in is equal in minus 1 over 2 plus the sum, okay, of here hn, okay, the sum from I is equal 1 till n over 2, okay, of f of a plus, or here, well, I can use I can use k, doesn't matter, let's use k, okay, k, 2k minus 1 multiplied by h, and the whole term, okay, it's the same formula. V zeta, it's the same formula. So you wonder how the same formula will give a different result. I will tell you why, because the only difference between the two programs is the same formula, the same algorithm, everything is, like I said, the first point and the last point. So if you change this value for I1 now, the I1 was HF of A for a rectangle, okay? At the first step here, what I mean by the I1 is the first step, okay? So if you change the formula for the first step here, okay, instead of HF of A, you use, okay, H over 2 F of A plus B, then you get the rectangle method. Okay, so at step n, you divide, so Hn is equal Hn minus 1 over 2, you divide H by 2. And like I said, in the program, you just make h is equal h by 2. And the number of points here, n, okay, is, or n is equal to n, where, okay, I can add n, but no, I don't want to complicate the formula, but n is equal to n, okay. So the number of points here get doubled at each time. So the number of points at the step n is 2 times the number of points at step n minus 1. And here, so you start by n equals 1 and by this formula. So basically, it's the same formula, it's the same method. It's not the same method, it's the same formula, it's the same algorithm. Okay, let's return on the algorithm here. All right, so إذا برجع على الالجوريثم بدي اشتغل على الباوربوينت.
Yes.
Okay, so this is all you have to do in order to compute with the trapezoidal method up to a given precision is, instead of I is equal h of a, you put I is equal h of a plus b over 2. Okay?
Okay.
H of a plus f of h f of a plus f of b over 2. So, and in this case, you get the trapezoidal integration. This stays the same. I mean, this is I over 2 plus h f of h. This is okay. Or this expression stays the same. Okay. The only difference is corresponds to the values of the starting point. Yeah. Instead of using hf of a, you use hf of a plus f of b over 2. يعني home. Okay, let's show you the program now. This was program. Okay, شايفين الماتلاب program. Okay.
Yes. Okay.
So here I had hf of a. Okay. So here, instead of using hf of a, I will use hf of a plus f of b. By here all same parentheses, and I divide by 2 here. I can divide by 2 here. Okay, so now we will save and we will run this program, and we will compare the number of iteration, and we'll see what we get. Wait, I have there's some mistake here. Just want to see if just a moment, there is some mistake somewhere. So minus 1. Okay. Okay. Let's here one can add the plus 1. Okay. So the expression is minus 1 here. 2k
Okay.
minus 1. Right. Let's recalculate this for the rectangle. Just see. Let's just like, okay, we'll comment this now. A, okay, phi is equal h by f of a. Now let's rerun this for the rectangle to see what we get as the number of iteration. So we get 16 for the number of iteration. That's why we get the wrong result here. Equals to, now we get 14. Okay, we get 14 for the number of iteration, and we get I1 equals 0.999. Okay. Now, if instead of using this, I use this. Okay. I get number of iteration equals 8. Yani I reduced by 2 the number of iteration just by changing the method. So I show you, okay? So if I comment this, I put, so this is the first step, yani. If you just change the value of the first step. So this is, I will run this, okay? Show you the value here for, let's share this new screen. Okay, you see, number of iteration equals 14. The integration is 0.9999. It should be 1. Okay, but as I said, I took an error of 1 minus 4 in absolute value. So that's why I got the result up to a precision of 1 minus 4. If I take, for example, 1 minus 6, okay, let's see what we get if we take 1 minus 6 here. Okay, so I1 is equal to 1, okay, because this is the maximum precision that the computer can show you 4 digits here. So, but it's up to 10 minus 6. And now let's look at the number of iteration. It's 21, right? It's 21. Now let's change it. Change the A instead of HF of A, let's input HF of A plus B over 2. And let's run it again and see what we get. So, okay. So now I have got 11 iteration, while before, for the rectangle, how many iteration I have? 21. Right, so I almost divide the number of iteration by 11, by 2. Okay, so I had 11 iteration for the rectangle, 21 for the rectangle, and 11 for the trapezoid. Of course, this depends on the precision. So the more you want your result to be accurate, the more the problem will, okay, the more you will have to do some iterations. But okay, it's the same program, so I didn't change anything. I just changed this line. okay, this line into this one. So the first step, the second steps remains the same, okay, and everything remains the same, all the program. So at every step, okay, we're dividing the step by 2 here. At each iteration, we're dividing the step by 2, multiplying the n by 2, and then we're doing the sum, okay, on all terms, so from 1 to n over 2, and 2k minus 1 multiplied by h, and then, okay, I1 is equals I over 2 plus, so this is the new I, the old I plus h multiplied by the sum of the f of xi, okay, such as xi is equal to 2k minus 1 with k equals 1 to n over 2. All right, any question corresponding to this?
No questions.
Okay. So, like I said, it's the same algorithm, it's the same program if you want to do an iteration for the trapezoid. The only difference would be in the first two values. So it's the mean value of the first and last value. The first, the rectangle left corner takes the first value, the right corner takes the last value, and this one is the mean value of the two. Plus.
Okay.
Now, let's see another method here. Okay. So the other methods, so 4, 5, I think it's pretty sure. 4, 2, 4, 3, 4, 4. Yeah. 4, 4. The Simpson method. Okay, so the Simpson method is that if we have, for example, here, so this is my interval, let's say AB, okay, and this is my function f of x, okay. This is x, okay. And we have, like before, okay, we have n sub-interval, all right, and n plus 1 points, okay. So n plus 1 points. So this would be my point x1, and this would be xn plus 1, and a equals x1, b is equal to xn plus 1. In the Simpson method, we consider each 2 points, each 3 points, and this x1, x2, x3, and we construct the Lagrange interpolation polynomial based on these 3 points. So, okay, we construct a Lagrange interpolation polynomial passing to these 3 points, and we calculate the area as, okay, the area of the integration of these, like this Lagrange polynomial. So for example here, if I have the point x2, x1, x3, okay, then I construct the Lagrange polynomial passing through the points x2, x1, and x3, and I integrate this Lagrange polynomial instead of integrating, okay, in the trapezoid, it's okay, the area under the line here. Instead of integrating the area under the line, you integrate the area under the trapezoid, the Lagrange polynomial. So it's the same thing here, okay? Okay, x3, x4, x5, etc. Okay, so these are okay. Okay, so the values, okay, of the Lagrange. Let's stop here. Okay, so let's take here b is equal. Okay, so let's stop here. So this is xn plus 1. So as you see here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 points, 9 points, 8 sub-interval, right? But how many Lagrange polynomial do you have? You have 4 Lagrange polynomial, okay? Because so this Lagrange polynomial constructed upon x2, x1, x3, x4, x3, x5, x6, x5, x6, x7, and x7, x8, x9. So, right? So now, so we approximate the integral as the sum of II. I write I2I here, okay? So I'll tell you why. With I going from 1 till n over 2, okay? Because if we have, like I said, n sub-interval, n is the number of intervals, a sub-interval. If you have n sub-interval, you have n here, okay, over 2 Lagrange polynomial, and you integrate. So this is the area under the Lagrange interpolation polynomial constructed upon the points x2i minus 1 f of x 2i minus 1, okay, x2i f of x 2i x of 2i plus 1 f of x 2i plus 1. Okay, يعني for I equals إذا عندي مثلا for example, okay, for n equals 8, okay, so you have, okay, the interpolation polynomial constructed upon here x2, okay, x1, x3. So here you get first Lagrange polynomial, okay, you get x4, x5, x6. So here in this case, here I equals 1, okay, so 2i minus 1, 2i plus 1, I equals 2, x6,
فوق x3 مش x5.
sorry here, so x2 so here it's no x4 x so just 1 minute. So yeah, x3 x5, okay, x6 x5 and x7 x8, okay, x9 and x7. So this is y equals 3, okay. So the first polynomial, second set, and fourth polynomial. So if you have 9 points, okay, you have 8 sub-interval, and you have 4, okay, polynomials that you can construct upon these points. Okay, so let's write this polynomial here. So I'll call the polynomial P2I, okay, as being the polynomial constructed upon these points. So if you remember, okay, it's the expression. So it's passing through the points here, f of xi to I plus minus 1, f of f to x to x to I minus 1, x to I plus 1, etc. So if you want to construct this, so this would be f of x to I minus 1 multiplied by here Li. I will call it this the first Lagrange polynomial, okay. The second Lagrange polynomial constructed on the 2i here, L2i, plus f of x2i plus 1 and 2i plus 1. So this would give me here f of x2i minus 1. So here I will have to take all the possible products, x, so it's x, okay, minus x to I by x minus x to I plus 1, okay, divided by x to I minus 1, okay, sorry, minus